Hmm. Okay. So, right, basically we encrypting cryptography. Huh?
No, I hope my voice is clear now.
Much better. एक बार फिर से माइक चेक कर रहा हूँ मैं आवाज आ रही है अभी ओके नाइस So let's start with the session. So we'll be covering cryptography in this session. Basically, an intro to cryptography. We won't go into details, not many details, but like, hmm, uh, yeah. I'm expecting that you will research. You will go deeper in these topics in your own time. This will be just an introduction to the topic. So, uh, this is the description on Wikipedia about cryptography. Cryptography is the practice and study of techniques for secure communication in the presence of adversarial behavior. So, what does adversarial behavior mean? It basically means uh, you want to you want to share some message to someone, but someone else can hear that message, and you want to encrypt the message in such a way such that even if the malicious person has heard your message, he cannot decode the decode or get the data inside the message, right? So yeah, so moving forward, we'll be working with this premise that we have two people, Alice and Bob. They want to talk, uh, but they can talk. They need to share sensitive information with each other. Uh, yeah. So we'll be working with this premise that there are two people, Alice and Bob, they want to talk, but Eve can eavesdrop on their conversation. Right. We'll denote Alice with A, Bob with B, and Eve with E. So now, uh, yeah. So we'll be like discovering methods how can Alice and Bob encrypt their messages so that Eve cannot get any information regarding what they're talking about. So, um, in the posters we did write modern cryptography. There is what traditionally there were many cipher schemes. Uh, uh, so like before the advent of computers, even like there even, in the past before the advent of computers, cryptography mainly used to study the cipher schemes. So um, what's the point of cipher schemes is you have beforehand agreed on a key and a message scheme, and now you are using that scheme to share messages with each other, uh, and you want to encrypt those messages so that even if someone discovers the data, they won't be able to decipher the message. So um, let's see. Um, See, you know how the internet works. There are servers which store like web pages and stuff, and we request data from those servers. Uh, right? We, Hello, hello. Yeah. Uh, we'll be first exploring some ciphers. See, in the current state, right? Current state of the internet, there are servers which store the data which we want, right? And we need to ask the servers to send that data to us, right? But as it turns out, like data at the end of the day travels in wires, right? If someone can intercept that data from the wire, right? So they can this is effectively the same situation. Say like A is the server, B is us, and A is some malicious actor which wants to access our data. Right? But we can't, and E can effectively intercept all the data since, well, the data essentially travels in wires, so someone can easily just wiretap the data. So we need to encrypt the data so that anyone listening for the data doesn't get the data basically. So before tackling the case of the internet, we tackle a simpler case. Let's say the parties have met once beforehand and they've decided on a key first, right? In case of internet, uh, like there are people across the globe. On the other side of globe, we can't meet first and decide on a key. Uh, Even that, right? So I mean, basically in this situation, in the case of internet, key sharing is also a major problem. We'll see how that is solved later. First, let's assume that we have decided on key. The two parties which need to talk have decided on a key before someone started intercepting the data, right? So how can they encrypt the data? Uh, One of the most simple solutions, practically canonical solution is this: like you just substitute single letters. ABC becomes BCD, hello becomes IFMP. Like you shift, you replace A with B, B with C, C with D, and so on. And let's say you replace Z with A, cyclically the shift these. This is a pretty obvious solution, uh, but this is very obvious solution, but there is a very obvious flaw in this, right? Uh, let's say, I mean, Alice and Bob have decided that they will shift their messages one step forward. When decrypting, they can simply shift their messages in the opposite direction to get whatever the others say, right? And Eve is hearing on these messages. Let's say if Eve Eve thinks that if Eve realizes that they are shifting their messages, how hard will it be for her to decrypt the messages, right? It will be very simple. Right? This type of cyclic shift is called Caesar. I mean, this is not Caesar cipher. Caesar cipher is the same item, but you shift 13 characters. So A goes to M and so on. Right? A goes to N, okay, and so on. Right? And like 13 shift is called rot 13. This scheme will be called rot 1. But anyway, uh, so I mean, one parameter of this system is the amount of characters shifted. Alice and Bob could have decided on one shift, or they could have decided to take like 3 or 4 character shift, right? So like even if Eve realizes that they are shifting their messages, she won't know the exact amount of shift, right? But say uh, uh, but she doesn't know the exact amount of shift. But can you think of a way in which Eve can decrypt the messages anyways without knowing the shift? So, I mean, yeah. So the shift can be at most 1 to 26, right? So, so Eve can try all those shifts. She can try shifting by 1 to up to 26 characters, 26 or 25, whatever operator number. Yeah. So she can just brute force this key being the shift in this case, right? So like shifting all the characters in the same direction is pretty weak because she can just brute force these shifts, right? So uh, based on a similar idea of substituting the characters, a better scheme would have been you replace Alice and Bob met beforehand, and they decided to replace some alphabet with some other alphabet. Like uh, yeah, so they decided to replace like ABCDF becomes HELO or something, right? So in this case, Eve cannot feasibly brute force the key. The reason being, to brute force the key, she would have to brute force all the possible values A will go to, then all the possible values B will go to, and so on and so forth. And that will become 26 factorial possible keys. So she will have to check all those numbers. As it turns out, 26 factorial is a number with 27 digits, and such numbers cannot be brute forced. Not feasibly brute forced. It can be brute forced, but not feasibly brute forced. Anyways, so this scheme is more secure than just shifting. But as it turns out, this can also be broken. Anyone with any ideas how this system will be broken? How can Eve realize which letters go to which letters? Anyone with ideas can write it in chat or maybe speak up. Hmm. So to break this encryption scheme, well, as it turns out, yeah, like okay, yeah, that also works. Uh, some short words like and, like you can obviously, like there are only two one-letter words like A and I. So if you see a single letter uh, surrounded by space, you can deduce it as either an A or I, so on and so forth. But yeah, yeah, that will work, and that will work. Yeah, there are also other ways. Basically, the easiest way is like the if. Array, anyways, yeah. So if we know that the message was in English language, and if we have accumulated many messages, right? So as it turns out, the words of any language follow some distribution, right? Uh, taken soon, right? So, for example, in specific case of English, this is the distribution: E being the most frequent, then T and A, and specifically in this pattern, like E is 12%, then E is 9%, so on and so forth, right? This chart was taken from Wikipedia. You can you can almost find most of these ideas on Wikipedia, and there are others. And then- so, like Eve, Eve collects many messages, turn finds its frequency distribution of letters, like basically take the letter counts, and then looks up them in the table, right? Uh, this method obviously is not foolproof, but she can get many characters. Like uh, the letter E will become obvious, letter T will become obvious, most probably, and after that, most gaps can be filled manually. Right. This is one technique. But there are much better techniques which automatically decode this. Right. Yeah. There is a website called decode.com, decode.fr, uh, which has a collection of many such solvers, and more importantly, along with the solvers, they also have the idea on what idea they work on. Right. So also in beginning of this discussion, we assumed that they were talking in English. Even if you didn't know that the underlying language was English, there is this thing called index of coincidence of a language, which is basically some formula which essentially acts as a fingerprint for the language. For example, uh, basically, yeah. For example, for English, English plain text, it it is around this number, in German this number, etc. etc. So there are ways to reduce information from even encrypted data. Mhm. So moving forward, uh, yeah, let's take a moment to look at Wigner cipher. The main problem with these two encryption schemes were uh, in in this encryption scheme we were shift. There was like only one parameter, the shift, which was encrypting the data. In in this case, even if uh, there were like 27 parameters we needed to brute force, 26 parameters. They were uh, if A was encrypted with H, then A will again encrypt it to H. So the structure of the underlying language was preserved. The underlying structure was preserved. You will see the same problem in AES CCP block mode. We'll be covering that soon, hopefully. But yeah. Uh, this is Wigner cipher. Wigner solves those problems by not sending same letter to same letter every time. Basically, uh, mm, I guess I will do that. Mm, So Wigner basically works like this. Uh, you first choose a key will act as shifts. If let's say the chosen key is just key, in fact, KEY, right? So a letter A will shift 0 0, B will shift 1, so on and so forth. For example, Z will shift 25 steps ahead, right? So if the message was ABC, right? And if you use this key, uh, K will shift A 10 times ahead. A will go to K, right? And E will shift the character 4 times ahead. So B will go to F and C will go to 24 times ahead with 327, and it ramps around to A. Uh, yeah. Anyways, so basically the benefit of this idea is that a same letter can go to different characters, right? So in this case, if the key is shorted, we can just repeat this. Okay. For example, H and K go to R, E and E go to I, L and Y go to J, but this L and K go to V. So even if the plaintext has the same letters, the cipher text could have different letters. Like so, this is this is better than monoalphabetic substitution in the sense that you can't just uh, whip up the frequencies and decode the message. So moving on, but yeah, then again, this is just a this is like a toy example. This is also very breakable. You can look up the methods. Hmm. Now, so yeah, so this is one time pad. I just okay. Right, one time pad. One time in one time pad, basically you have a message, right? You have a message you need to encode. So the both parties will decide on a key beforehand. Key must be This key should satisfy a few properties. These few properties being its length must be greater than of messages. It should be it should be random, and this key should never be reused again. The one from one time pad comes from that this key should never be reused again. And the way of encrypting in one time pad is using the bitwise OR operation. So what bitwise OR does, basically, if bitwise OR takes 2 bits, and if they are different, it outputs one. This is bitwise OR. Uh, yeah. So as it turns out, this encryption, the only way to break this encryption scheme, given that key satisfies these constraints, that it is never used again, we basically need to brute force the key. So yeah. Also, brute forcing the key is where it's very computationally intensive. Say if the key has 50 bits, right? 50 bits means like 50 by 8, around 6 bytes, right? So if the password was even like 6 characters, right? So it it will take it will be around the 2 2 raised to power 50 possible 2 raised to power 50 basically, which I would estimate is around 10 to 12 or something. I don't know. Anyways, 12 or 14. Anyways, so basically, brute forcing the key is not feasible, right? So yeah, in one time pad, basically you decide on a key beforehand. that key should never be reused, uh, and you encrypt with that key, right? So this is very strong. Right? In our situation, Elsa and Bob wanted to communicate. They have decided on a key beforehand, right? But once they encrypt, they can never use that key again. Can you suggest a method that one-time pad can use for communication between two parties? Let me repeat the question. Uh, in in one-time pad, the key generated can only be used once, right? But we want to encrypt messages multiple times. So can you suggest a method in which Alice and Bob can communicate using this one-time pad encryption scheme? Okay, the new key every time they send a message idea. Well, they are only allowed. See, the point being, Alice and Bob have met once before, and now every after which everything they talk about, Eve can hear, right? So how will they share the key among themselves if they make a new key? I mean, the idea is obviously correct. We need to make a new key every time. Uh, they could have made multiple keys initially, but problem with that idea is like basically we need to send many messages, so we don't know the number of messages we'll talk about. So yeah, yeah, this idea basically. Uh, Whenever, let's say Alice encrypted her message, she is sending it to Bob, uh, and Alice sends a message. Before sending the message, she appends the new key to the old message and then encrypts it. Then Bob decrypts it and gets the key for the next set of exchange. Next set of exchange. Yeah. Hmm. So I have been talking about like one-time pad will be very weak if it is used. Uh, this was a challenge. I'm pretty sure I used this as a challenge in something techniques or something. I don't remember, but yeah. So you can research about this. Why will OTP will be weakened? Uh, this basically boils down to the same idea, uh, same problem which monoalphabetic substitution face. Like same pair will result in same pair. Actually, not monoalphabetic Vigneer, right? In Vigneer, effectively, the pair of characters encodes a new character, right? So this will face a similar problem if the key is reused. So you can think about that. That the second is Now let's discuss about AES. AES is similar scheme. I mean similar in the sense that it is a symmetric cipher. Symmetric meaning you need a single key. This key is used for both encryption and decryption algorithms. So let's just see some. Yeah, as it turns out, AES is a bit complicated. Uh, Not complicated, but it has many steps. Right. You first take the gate. If you want an intuition for AES effectively just mixes up the data, but it does so. And to decode it, basically you just need to apply the AES algorithm in reverse using the key, and then you can decode it. But yeah, the main factor due to AES is so widely spread and used is it uses very simple instructions, so it is easier to easier to implement it on hardware, and and it is and to decrypt it, there is no way to decrypt it other than brute forcing the key if you don't know the key, right? Also, AES is a block cipher, so basically you split the plain text into blocks and you encrypt the blocks individually, right? This is AES. Uh, but as it turns, yeah. So AES is a block cipher. Let's say this is a message you need to encrypt. You split into blocks of predefined size, chunks of predefined size, and use the key somehow uh, to encrypt it, right? So you take this block, use this key somehow, and create the ciphertext, right? Now, what modes of operation mean? Yeah. So what modes of operation mean is you have encrypted this block, right? Now, how will you encrypt this block? You can One option is you just use this same key again, encrypt this block, use same key again, encrypt all blocks. So you encrypt all blocks with the same key. One method is that. Other, as it turns out, okay, let's first discuss what is the problem with this method. This method is called ECB mode, ECB electronic code book. Um, you take plain text, uh, basically actually, I mean, these modes of encryption can be applied to any block cipher thing, right? In this case, this thing corresponds to our AES algorithm, which takes a block of text and converts it into something else, given a single key, right? Uh, for this thing, right? But of course, ECB mode can be used for any such encryption algorithm, which takes one thing, takes a key, and produces a ciphertext. This is ECB mode being uh, that this thing is is what you call it, independent. These blocks are independently encoded using the same key. Now, the problem with this is same, not same, but similar to what the problem was in monoalphabetic substitution. Mhm. Say you have some block, some block of some block, and this same block is repeated here, right? Since you are using the same key, AES will produce same ciphertext, right? So let's say Eve gets the whole ciphertext. She can only see the ciphertext. See, she sees that this block and this block contain the same data. So she can deduce that this plain text block and this plain text block must have contained the exact same data. So just given the ciphertext, Eve has uh, Eve has Eve has gained some knowledge about the plain text, right? This is not desirable in a crypto system, right? Just by seeing ciphertext, you gain some information about plain text without any idea of the key, right? This is not a desirable feature for crypto. Uh-huh. So one of the most famous example of this is called the ECB penguin. You basically uh, take a photo, take any photo, uh, and you encrypt it using AES ECB. In fact, not necessarily AES, any ECB, any block cipher using ECB mode of operation. Even though the data is encrypted, we can this black color will go to a similar color. This background white color will go to a similar color, and this white color, for example, goes to a similar color, right? So just looking at this image, you can deduce that this background must have been same. This thing would have been same. This thing would have been same. So you can deduce what this is. I mean what the input image was, what the plain text was, just by looking at the output. Right? You don't have any information about which key was used, but you can deduce information. So uh, this is very weak in this sense, right? It is strong that you cannot brute force a message without knowing the key for a single block. Like you don't know what exact color this was, but you know whatever this color was, the whole this thing was the same, right? So that was one mode of operation that you individually use the keys. This yeah, oh also uh, it stands for electronic code book. The reason being, I guess I'll take this moment to discuss about difference between encrypting and encoding. They sound same, but they are a bit different. In encrypting, you take the data, you have a key or something, and you change the data, right? And to so the main difference from encrypting and encoding is in encoding you also take the data and change the data, right? But in encrypting, uh, you should not be able to go back without knowing this key encrypting. But encoding is just converting the data into different form. So you can just go back to data without knowing what the data was or anything, right? So for example, ASCII is an encoding scheme. In ASCII, basically A becomes the number 65, B becomes 66. This is just an encoding scheme. If you are given these numbers, you can easily just convert them to A, B, and so on and so forth. Mm, and that. Mm. So this is the difference between encrypting and encoding. The electronic code book ECB mode. So so this basically means you have a data, the key sends it to something, right? So effectively you have just a table, right? You have a table that if I have this block, this goes to this block. If I have this block, this goes to this block, something, right? So you have effectively an code book which encodes the data given the key and electronic because it is electronic. Anyways, the other mode being CBC mode. In CBC mode, what you take the plain text, you basically XOR it with some another IV. This IV may be public, may not be public, doesn't really matter. But you take the key, you Basically, this part is similar to whatever it was. Yeah, yeah, better. Yes. Hmm. CBC mode, you take the plain text, you first create the first block of ciphertext, right? But this key, the second for the next step key, okay, I guess, and basically you have IV, you sort it, you get the next ciphertext, but this ciphertext is chained with this plain text. You again sort this thing, right? So so what basically happens, right? If even if this ciphertext is same as this ciphertext, right? This doesn't mean that this plaintext is same as this plaintext. Why? Because basically there basically you have sorted it with something else. Sorting is just one time pad. So you have created a new, you have just one, basically you take the plaintext, you one time pad it with the previous ciphertext and then encrypt it using AES. Reversing this is simple. You take the ciphertext, you decrypt it using this key, whatever comes. You sort it with this ciphertext. You get the plain text back, right? So in this mode of operation, this same block of input goes to different block of input depending on the previous output as well, right? So this is much more secure than the other option. Reason being, even if you change a single character in the first block, it will affect all of the blocks in the future. Okay. So yeah, ECB is usually you can see this in CPS because it is so weak. CBC is the most standard mode. It is you it is it has most applications. There are various other modes like cipher feedback mode in which you do this. You can look these up in your own time. These are interesting, pretty interesting. Also, most of the things I'm talking about in modern crypto systems, from one-time pad to ECB, etc., EPS, etc. You can practice you can practice with these questions on cryptohack.org. This very nice website with a minimal UI and nice challenges to understand the crypto concepts. Cryptography. So yeah, all of our previous discussion is okay. Before starting asymmetric encryption, uh, does anyone have any questions or any doubts? Anything?
No, there is someone who has asked a question.
Uh, okay, okay, I guess. Okay, okay. I did report that. Okay, okay. So okay, let me how to solve etc. etc. Okay. Um.
Now try to make it something like थोड़ा bigger बनाने की try करो text. ठीक है ठीक है. Box box. बस बस.
This is just a Python. Python terminal. Wait a minute. Is my screen visible now? This terminal. Hello.
Yes, it is visible.
So see. Okay. So you will in the last this session We discussed about different encoding schemes, base64, etc., etc. Right. So in Python, you can work with raw bytes, but with raw bytes like this, right? Raw bytes basically byte strings. This is a string, right? This is basically bytes. For example, if you take A0, this is 97, 97 because uh, this is encoded in SP, returns a Unicode code and for one character string, right? Okay. So this is A. And say if we take B anything, B, let's say it's just hell. Uh, yeah, B is let's say this, right? So what XORing two strings means, I mean, if you do this, which is this is Python XOR, this will fail because XOR, yeah, basically it can't do this for bytes. But what XORing 2 bytes mean? I mean, you can do this. You can do A's or B's, right? This will give you the next byte, right? So we can implement XOR like this, where A is bytes, B is bytes. Uh, Now this is a okay. You can do this always. N1 is equals to V1. So um, mm, mm, mm. Oh, max AB me max N1 into yes. Right. So this is the sort. If I do this like this, what are you? So these are basically byte values. This nine, this nine being the XOR of A and H. This this 11 being the XOR of B and I. This 11 being the XOR of C and H, etc. Right. So basically, if you are using Python or any such thing in which you can work with raw bytes, the XOR will effectively be you take the byte, you XOR with the corresponding byte, right? In Python specifically, this structure will work for XORs. As it turns out, you don't really need to implement this yourself. Uh, of course, Python doesn't have inbuilt this, but there is a very famous library called Pawn. So in this, you have XOR, Pawn tools library, basically, yeah. And this XOR is very nice. You can decide how to, like, you have to take the shorter one, longer one, left one, right one, or wrap around. You can decide that as well. Mm. So yeah, you can use the library implementation, this thing, which is basically, I'm pretty sure you can just do this. Yeah. So you can just do pip install pawn tools, install it, and use the library in implementation. Right? But at the same time, it's not that hard to implement it from the ground up. So, um, so that was basically how to implement it in Python or any language in which you can work with bytes. Even if you cannot work with bytes, you can just treat it as character array or something. Hmm. So the XOR operator basically does takes two numbers and returns their XOR. This so you just have to treat this as two characters. Another way to implement this without using byte arrays would have been this. Let me show you. Even if A and B are strings, if you want to work on strings, assuming you are working with ASCII string, etc., you can just do this rather than taking X or B. I mean, uh, this will result in error. You take the order. You basically order is just converting it to the integer, and rather than returning this, you can return this. Then you can just do this one. So this becomes this. Uh, um, I guess since okay, I guess I'll also show that ECB penguin demo. This is the original image. Uh, I did gloss over this in the explanation, but this image needs to be in ppm format. I mean, not ppm format, in any format where like the pixel correspond to a single block. Uh, I'm pretty sure he covered this while covering forensic and stuff. In PNG format, the individual pixels are not stored as pixels. They are basically compressed, right? Uh, in PNG or something, I don't remember exactly, but yeah. Usually in modern image formats, images are compressed for depth, saving space, etc. Right? So for this demo to work, the image should be in format where the pixel is pixel. For example, I'm pretty sure I can do this. So, so the image is essentially a header, which tells you the size and color scheme of the image, followed by the raw bytes representing the color. Right. So basically, FFF being white or something like that. So essentially, color is uh, stored as contiguous data, not compressed or any other thing. Right. For example, in red or white as well. So after encrypt, okay, I guess I'll also show how to do this in Cloud. I don't know. Can use anything. हाँ, अरे अरे so so basically using this key, uh, I mean, okay, this random key was used. I guess I should do that here. So using this key, you get this sort of penguin from uh, this image. So you can still make out the shape of this image, right? Um, Anything you would like to be seen, you would like to see. If not, then we will be moving on to asymmetric encryption schemes. Okay, then. So yeah, in these examples, we have assumed that Alice and Bob initially shared a key, right? But for example, if you and I wanted to share a key, we are probably on campus, we can probably meet up and share that. But daily on the internet, we need to talk. Our computers need to talk to a lot of other computers to get the data we need, right? So how can we ensure the safe? How can we ensure that this data is not compromised, right? Or this data has not been leaked to someone else, right? So we need to share a key, but we need to share a key such a way that so that like we can publicly share the keys, right? Or or we can try something else. This asymmetric encryption is something else. We'll see how to share key using asymmetric encryption type structures. But yeah, right. So yeah, so yeah. In asymmetric encryption, yeah, we change the technique. Hmm. Asymmetric encryption, any party, let's say Alice and Bob want to share a data. Alice will generate a key pair uh, con- uh, containing a private part, a private key, and a public key, right? Anyways, let's just go with Zoom. Anyways, Alice will generate a private key and public key. Bob will generate a private key and public key, right? So now what is special about this system? The public key will be public. Anyone can see this, right? So Bob, uh, we also have uh, E, E. Hmm. So Alice can, what information Alice has? Alice has her private key, her public key, and Bob's public key. Alice knows these. Bob knows his private key, his public key, and Alice's public key. Eve knows Alice's public key and Bob's public key, right? So, what is special about asymmetric encryption is you can either encrypt the data, basically, you can encrypt your data with private key and decrypt with public key. This allows for signing your messages, right? Or, uh, okay, rather than talking in abstract terms, let us talk in some concrete situation itself, right? Let's say, uh, okay, let's say Bob wants to send a message to Alice, right? Bob sees her public key. Bob knows her public key. So what Bob will do, uh, Bob will take the message, encrypt it using some asymmetric, asymmetric algorithm using the public key of Alice, right? And gets the data. This data is sent to Alice, and Alice uses a private key to decrypt this. So so what? Right? Okay, I guess I know. Message public key of Alice से encrypt किया, encrypted. Now ये Alice को गया, साथ साथ Eve भी intercept कर सकती है ये data, right? But but जो Alice होगी, वो अपनी प्राइवेट की को यूज करके इस डेटा को डिक्रिप्ट करके जो मैसेज था उसको रिकवर कर लेगी, और ईव के पास क्योंकि एलिस का प्राइवेट की नहीं है, वो उसको डिक्रिप्ट नहीं कर सकती. सो अगर हम लोग ऐसा, हमारे पास कोई ऐसा सिस्टम है कि हम एक की से इंक्रिप्ट करके दूसरी की से डिक्रिप्ट कर सकते हैं, और ये डिक्रिप्शन सिर्फ सिर्फ मतलब इसी स्पेसिफिक की से हो सकेगा, तो हम लोग ऐसा कुछ सिस्टम यूज कर सकते हैं, ठीक है। सो दिस इज बेसिकली एसिमेट्रिक इंक्रिप्शन। सो इन दिस एसिमेट्रिक इंक्रिप्शन हमारा जो की शेयरिंग वाला प्रॉब्लम था कि इसमें फॉर एग्जांपल वी नीडेड टू प्री शेयर द की अमंग एलिस एंड बॉब, वो प्रॉब्लम हमारा सॉल्व हो जाता है, हमें कभी की शेयर करने की जरूरत नहीं पड़ेगी, हम सिर्फ एक एक की को पब्लिक कर देंगे तो हमारा काम चल जाता है। आरएसए इन पर्टिकुलर कैसे काम करता है वो देखते हैं, किस कारण से काम करता है। एक्चुअली आरएसए की डिटेल में जाने से पहले इसके बारे में, इसमें इस आइडिया में कुछ डाउट है क्या कि मतलब एसिमेट्रिक है क्या? ओके आई गेस। Actually, rather than writing this, I can just show it. So the core idea of RSA, why RSA works is, well, because A times B is equal to B times A. This is the basic principle of RSA. Now, how exactly? This is how exactly. Right. I probably can't write on this. Anyways. So to encrypt the message, what you do is to say Bob wants to send a message M to Alice, right? So for RSA, you have a number. Okay, so let's go into details of RSA. Alice needs to have a private key public key pair for the asymmetric crypto system. So what exactly is private key? Alice's private key consists of two digits, N and E. E is usually 2 to the power 16 plus 1 is 65537. E is usually this number. E can be almost anything, not one. Why not one? We will see soon. But E, okay. And N is a product of exactly two primes, P and Q. So we have P times Q is equal to N, where P and Q are primes, where E is equal to 216 plus 1. So this is Alice's public key. Al- Okay, this is public information. What a private key consists? A private key is called D. It is inverse of E modulo phi of N. What phi is? I mean, I will not be going deep into these facts, but you can read up about these on a lot of places. Let me just explain what it is, basically. Then open to this number. Yeah, yeah. So I have n is equal to q times q. I have e is equal to some number, right? So if how encryption works is you if this message m is needed to encrypt it, you raise it to eth power and you take its modulo n. Okay, modulo basically means remainder. I'm coming this to a bit late, but anyways, modulo means remainder. Okay. Now, how to decrypt this? To decrypt this, whatever ciphertext you have received, you raise it to d power, d being your private key, right? And then you take it modulo n. This will be message. Why will this be message? The ciphertext you have received is n key power e. Now you are raising it to dth power. This basically becomes m key power e times d, and you want to take it modulo m. As it turns out, there is something called Euler's uh, Euler's torsion function. It basically gives you the number of numbers less than n which are not which are co-prime with n basically. So this thing is called phi of n. This has special property that if you take any number, you raise it to phi of n. This number will this number will give the same remainder as a when taking modulo n. So phi has this property. So so if if we can ensure that ed is congruent to 1 modulo phi of n, then we will be done. So we basically need ed is congruent to 1 modulo phi of n. And this is exactly the condition which by which we define d. Phi of n for since n is pq, phi of n is p minus 1 times q minus 1. You can uh, you can read up about phi, what is phi of and why it is the way it is. So essentially, uh, without if without seeing the mathematics, what RSA does or what any asymmetric scheme does, you have a message, you lock it with one key, and this key is public. But you can unlock it with only a single key corresponding to this key, and this key is private to whoever is receiving this message. Okay. But this thing has a problem still. Let's say uh, Eve. Let's say Eve has intercept. Eve has okay. Let's just work with Eve. This system works like B sends a message, but Eve receives that message and Eve forwards that message to Eve, right? So what Eve can do is just use her. Eve can create her private key public pair. She can or she can use she can use Alice's public key to encrypt any arbitrary message and send that to Alice. What? How can Alice confirm that message came from Bob and not from Eve? So basically, how can one ensure a message, right? So what we'll see is signing now. How can one sign a message that and right? So what? So basically, Bob needs to send a message to Alice in such a way so that he can ensure that message came from him. So what Bob can do is whatever message Bob needs to send, right? He will append append his sign to end of it. How can he append his sign? Uh, let's say just let's say Bob. He does he. I mean, the initial idea will be you have a message, you append let's append Bob, you send that to Alice. But obviously, this doesn't work. I mean, you append and then encrypt it with RSA because Eve can simply just append her random message M2 and just write Bob and send to Alice. So this way doesn't work. But what works is Bob, rather than appending just his name, Bob encrypts this with his private key, right? Bob encrypts this with D and then appends it, and then encrypts whole of this with Alice's public key. Now, when Alice receives the data, right, she just decrypts this with her private key. She receives message and some data at the end. Now, this signature can be decoded with Bob's public key. Alice has Bob's public key, so this can be decoded with Bob's public key. So she can decode this message and check if the message says it is from Bob, etc. Also, this message can include other information like the total length of message, etc. To even reduce the scope of tampering possible with the message. So this asymmetric system also helps in signing messages, and of course encryption works, right? So this is the problem with this approach is that compute the computations in RSA are expensive. In the best case scenario, you have of the order of log-n, uh, basically log-n-ish computations, which are exponentiation, which are expensive. So this can be slow. The way to right. So asymmetric encryption can be slow. Now we will see how we can use this similar concept to key share. Okay. So basically, now the situation is Alice and Bob want to share a key first, then use that key to let's use something like AES to encrypt their message channel or something, right? So Alice and Bob want to share a key. How they can share a key is let's say they have decided on G, like this is some standard G, right? G, just imagine this is 2, right? So Alice will choose a random number A, Bob will choose a random number B, right? If Alice wants to talk to Bob, Alice sends 2 to power A to Bob, right? Now Bob takes this and Bob sees that Alice has sent him something. Bob sends Alice 2 to power B, right? So now Alice has 2 to power B and A, and Bob has 2 to power A and B. So what they can do is Alice takes this and computes its A power. Bob takes this and computes its B power, right? So both of them get 2 to power A, 2 to power B. Now you may be thinking, if we were just sharing 2 to the power A, right? This system wouldn't be secure. For example, Eve can just see Alice has shared 2 to the power A. So her secret A must be log base 2 of whatever this was shared to the power A. So her secret must be A. But but we don't share just 2 to the power A. We share 2 to the power A modulo some big prime. As it turns out, taking logarithm modulo something is very hard problem in most cases. In some special cases, this may be very easy, but yeah, in usually cases, this log is called like discrete log. This problem is very hard, and that is the reason why RSA is like not easily breakable. Breaking RSA is equivalent to factoring the number, factoring the public key, right? And factoring large numbers is very hard. So yeah, if the number can be factored or once and or maybe there is a database for if if the factors can be found in a database, then RSA is very trivial to decrypt, right? That was RSO and any stuff. Right? So basically, after this sharing of key and things, both Alice and Bob have some common number. This common number then can be used to generate a new key. Let me recap this. Let me just yeah, I can just do an page. So what basically we do? Alice generates a secret A, Bob generates a secret B. Alice sends G की power A modulo some P, some public key or something. G की power A P. Bob sends Alice G की power B mod P. Now Eve can see both of these. Eve has seen कि Bob has sent this thing and Alice has sent this thing. But even if knowing G की power B, Eve cannot deduce the value of B. And even knowing G की power A, Eve cannot deduce the value of A. This is the fact which is strengthening, which is basically the strength behind this thing. So now after they have seen this, what Alice does is whatever she has received, she raises it to eighth power. Bob does the same thing. It has received A and Bob raises it to be B8th power. So Alice now has AB, Bob has BA. Now as BA and AB are same, both have common shared secret. So both have gotten their secret. So they can just create a key using this secret. Okay. And Eve, even after seeing all this data, she doesn't know the secret because she neither has A, neither has B. So now Alice and Bob can just use AES to encrypt their conversation because AES is faster than RSA, etc. Faster in the sense less expensive. Anyways. Also this procedure which I have described is Diffie-Hellman key exchange. This is not the only possible procedure. There are a lot of other structure which can be used for key exchange, etc.
आई गेस उसका माइक थोड़ा ख़राब है। सो गाइस अभी तक जो बताया है उन्होंने समझ में आया होगा, आई होप सो। एंड रैप अप करते सेशन के रिसोर्सेज जो है उसमें मेंशन्ड है। अगर आप लोगों को कुछ क्वेश्चंस है तो आप पूछ सकते हो अभी चैट में। ही वुड बी देयर टू आंसर दिस क्वेश्चंस एंड फील फ्री टू डीएम हिम। व्हाट्सएप में आप डीएम कर सकते हो उसे। या फिर हम लोग भी है व्हाट्सएप पे अवेलेबल। अगर आपको कुछ भी डाउट आता है इसके रिगार्डिंग तो आप पूछ सकते हैं। एंड दैट्स इट फॉर टुडे। अगर आपको कुछ पूछना तो आप पूछ सकते हैं चैट में। Ankit, do you want to say anything? ओके, सो रिकॉर्डिंग जो है इस सेशन की वो अवेलेबल हो जाएगी आपको इसी डेमो प्रॉब्लम। डेमो प्रॉब्लम ऑफ व्हाट? अच्छा, डेमो प्रॉब्लम आप बोल रहे हैं वेबसाइट पर। तो या मैं उससे बात कर लूँगा। वी विल बी मेकिंग दो दैट प्रॉब्लम। आई थिंक यू आर रेफरिंग टू दैट CTF वाली साइट जो हमने बना रखी है उसके रिगार्डिंग। सो वहाँ पे प्रॉब्लम अप हो जाएगी रिगार्डिंग एनी क्रिप्टोग्राफी के बारे में। और जो रिकॉर्डिंग है इस सेशन की वो आपको प्रोवाइड कर दी जाएगी। इट विल बी प्रोवाइडेड ऑन द इवेंट्स पेज ऑफ दिस चैप्टर IIT BHU इन द गूगल डेवलपर क्लब वाले वेबसाइट पर। एंड बाकी जो इन्फॉर्मेशन है लाइक वेब आपका स्लाइड्स और वगैरह वो भी आपकी अवेलेबल हो जाएगी उधर ही। एंड कॉप्स का जो चैनल है उस पे ये जो रिकॉर्डिंग है वो अपडेटेड है प्लेलिस्ट में। लर्न टू हैक सीरीज इस सीरीज़ का नाम है। एंड वी विल बी कमिंग अप विद अ सिमिलर काइंड ऑफ वर्कशॉप्स इन द further days. So be alert to the notifications. And that's it for today. Thank you.